They said LFP batteries would last 20 years, yet 10% of it died in just 3 months. What is going on? Manufacturers claim LFP batteries can last up to 1 million kilometers. But on social media, countless users report losing 10% of their range before even reaching 10,000 kilometers. So who is telling the truth? The glossy laboratory charts, or the driver stranded with an empty battery? In this video, we put all biases aside and analyze a massive dataset, from Uber drivers and taxi fleets to scientific papers and real service records, to finally answer this question. Is the LFP battery truly immortal, or is it simply a well-marketed illusion? Let's begin. Let's take a closer look at the graph. Here we see two curves, labeled A and B. Curve B represents the theoretical lifespan of LFP batteries. It is so flat and stable that it takes more than 4,000 charge cycles to drop to 80% state of health. For an average passenger vehicle, that translates to around 1.6 million kilometers of driving. Curve A, on the other hand, represents conventional NMC batteries. They retire much earlier, at roughly 2,000 cycles. On paper, the promise of the immortal LFP battery is built entirely on this graph. But here's the problem. These graphs are drawn under perfect laboratory conditions, controlled temperatures, and ideal charging behavior. Real life is not a laboratory. In the real world, physical limitations and software-related issues prevent most users from ever reaching this theoretical lifespan. And when we stop listening to theory and start listening to drivers, a very different picture emerges. On social platforms, users complain, "My car won't charge properly in winter. My range suddenly dropped by 10%. These complaints reveal a fundamental mismatch between user expectations and the actual behavior of the technology. When we examine the technical root of these issues, we discover something surprising. In many cases, the problem isn't lithium-ion chemistry at all. It's the software trying to measure it, the Battery Management System, or BMS. This slide proves that the issue is not chemistry, but mathematics. Here you see the discharge voltage curves of NMC and LFP batteries. In NMC batteries, voltage drops steadily as charge decreases, sliding smoothly down from around 4.0 volts. This allows the car to confidently say, "My battery is at 50%. But now look at the orange line, the LFP battery. From 80% down to 30%, the voltage remains almost perfectly flat between 3.2 and 3.3 volts. This is known as the voltage blindness zone. Because voltage barely changes, the BMS cannot tell whether the battery is at 70% or 40% based on voltage alone. Instead, it estimates charge by counting energy flowing in and out. Over time, small errors accumulate. And this, not chemistry, is the real reason behind sudden range drops. This phenomenon is called phantom degradation. A sudden 10% drop on your dashboard is not physical damage. It's a software correction. Here's how it happens. Step 1. Due to voltage blindness, the BMS underestimates the battery's true charge. Even when the battery is actually full, it may display only 90%, showing, for example, 380 kilometers of range. Step 2. You charge the car to 100% and let it rest. Cell balancing occurs, and the system finally sees the voltage peak. Step 3. The BMS recalculates capacity, and the lost range suddenly returns, jumping back to 418 kilometers. Nothing was repaired. Nothing was recovered. It was never gone. Another reason LFP batteries appear to degrade faster lies in hidden buffer capacity. To protect the more fragile NMC chemistry, manufacturers hide large safety buffers at the top and bottom of usable capacity. As the battery ages, these buffers are consumed, masking degradation from the user. In short, NMC hides its losses. LFP batteries are structurally tougher, so manufacturers use much smaller buffers. This transparency means every 1% loss is immediately visible. A 5% loss in an NMC battery may go unnoticed. The same loss in an LFP battery hits the screen instantly. This doesn't make LFP worse, it makes it honest. When we look at battery health over time, we encounter the first-year shock. The red zone on the graph, the panic zone, represents the first 6 to 12 months. During this period, a solid electrolyte interface, or SEI layer, forms on the anode. This is chemically unavoidable and permanently consumes about 3% of capacity. Users see this drop, panic, and assume degradation will continue at the same pace. But it doesn't. Once the battery enters the green stability zone, degradation flattens and remains stable for years. Data from Geotab and BDI confirms this. The early loss is not failure, it's chemical settling. LFP batteries do have a thermodynamic Achilles heel: cold weather. At 10 degrees Celsius, LFP batteries can lose up to 40% of usable range, compared to around 25% for NMC. Ion conductivity drops much more sharply in the cold. Charging behavior shows the same pattern. Without preheating, cold LFP batteries struggle to accept charge, almost flatlining. But here's the key point. This is performance loss, not health loss. When the battery warms up, the range comes back. The battery isn't dying, it's just cold. Battery aging doesn't only happen while driving. This is known as calendar aging. Studies show that around 60% of total battery degradation comes from time itself, chemical reactions that occur while the car is parked. Only 40% comes from charge cycles. Even an unused LFP battery can lose 1 to 2% capacity per year if stored at high charge and high temperature. Here we reach a fundamental conflict: software accuracy versus chemical health. The BMS needs occasional 100% charges to measure correctly, but chemistry tells us that staying at 100% creates stress. Manufacturers like Tesla resolve this by recommending charging to 100% once per week. Every day stresses chemistry. Never doing it blinds the software. Balance is the solution. Now let's look at real-world proof. An Uber driver's Tesla Model 3, heavily used and frequently fast-charged, shows only 5% degradation after 177,000 kilometers. Despite common claims, LFP performs exceptionally well. At roughly 2.5% degradation per year, this battery could still retain over 80% capacity at 1 million kilometers. This data is independently verified and extremely difficult to ignore. BYD taxi fleets in Shenzhen tell the same story. At 300,000 kilometers, vehicles retain 93% battery health. At 500,000 kilometers, many remain above 80%. Some have exceeded 700,000 kilometers on their original battery. Most combustion engines don't even survive half that distance. Large-scale Geotab data reveals what's known as the flatline effect. After the initial drop in the first 20,000 to 30,000 kilometers, degradation nearly stops. A battery at 50,000 kilometers looks almost identical to one at 150,000 kilometers. This is where users say, degradation stopped. So why doesn't anyone actually reach 4,000 cycles? Because of time. A typical driver covering 20,000 kilometers per year would need 880 years to get there. A taxi driver driving 200,000 kilometers per year could reach it in 8. These batteries simply haven't been around long enough for private users to hit the limit. There is no perfect battery, only the right battery for the right use case. LFP excels in safety, calendar life, and cycle life. NMC shines in cold weather, energy density, and performance. If you live in extreme cold or demand maximum performance, NMC may be the better choice. For most users, however, LFP is more than enough.